So we have flat plate and it is subject to a tensile force of 5 kilonewton. You can see from the figure, and it is having a fillet region. It's not a plate of uniform cross section. It is having step part, and it's having a fillet region of radius 5. You can see, and after the fillet region, there is a central hole having diameter 15 mm. Can see, and this 5 kilonewton is acting on the fourth side tensile force. We have to determine the thickness of the plate. And the material they have mentioned is gray cast iron FG200. So FG200, we already know that 200 specifies maximum ultimate stress. So we have the condition, various conditions that it is applying a force of 5 kilonewton. We have to design. So basically, we are designing. Right? We have to determine the thickness of the plate that I have to manufacture. If I am applying a force of 5 kilonewton and it have a center hole, and there is a fillet radius is 5, and the ultimate stress of the material is 200. So how much thickness, safe thickness must it to be designed, having considering factor of safety 2.5. So we have to find by including all these parameters, we have to find the thickness of the plate. So let's look at the solution. So so this problem has to be solved in two ways. The first way is we'll be excluding the central hole on the shaft. So if I exclude the central hole on the shaft, we having a fillet radius shaft, stepped shaft. So and we know how to solve this problem. We have done this problem already done this problem in this previous problem. We have done this problem, and 5 kilonewton force is acting on both sides. You can see. So how do you solve this problem? We are not having momentum is not applied. We have the force is applied. Okay, it's not momentum. This force is applied, and capillary distance, overall diameter is 45, and the step diameter having small d as 30. And here we will be marking it as B based on different notation on different data books. So B means this distance, that is 45 mm, we already know, and small b is the step diameter, this diametrical distance, that is 30 mm, and R is the small r is the fillet radius, that is already given the question 5 mm. So the formula to find axial load condition for a shaft is maximum stress. How to find the maximum stress is this formula, F by into KT. So we need to have the value of F. We know how to find the area. We don't know the value of thickness, even though I can write it as thickness into B. Okay. So the reason why using small b instead of capital B is because of fillet radius. We have to consider this part. This is the point of stress concentration. The fillet part will be having stress concentration, so I need to consider only this part. So the area will be, but the diameter distance will be this part. Okay, so thickness into B. That will be the area. It will be 30 mm square. This T we have to find at the end. That is what they asked in the question. So if you check the data book, corresponding data book, you can see these types of shaft. You need to find the value of small r b and small r by b and a capital B by b. And if you have this both two value, we can find it by. I will show you. You can find it by this. You know, this this graph. This is the condition, and if you have the corresponding, we know the value small r b and capital B by B. So corresponding, if you plot, you get the value of KT. Okay, so I got the value of KT is 1.8 from the graph. So all I have to do is substitute it in this equation to find the maximum stress developed for the tiller region. So by substituting the equation, we got the value of maximum stress of the fillet region as 300 by T. So one for the first part has finished. Next, we have to consider that whole region alone. Because these two together combine the given figure of the question. And if you take the second part individually, we already know this case, right? And flat plate having center hole, having axial load, etc. at both, and we have done this part separately. So how do you find area? Area is there is a hole right down here, so we cannot include that part. So B minus A. A means this diametrical distance 15. So that is 30 minus 15 because you cannot use consider this hole. you have to consider the area excluding the hole. Okay, that's the part where the air stress is developing. So that into thickness, as usual the previous one. Basically, the breadth into thickness, but since there is a hole there, you have to exclude that part. So in this flat plate having axial load condition, we need to find the values A by B and just A by B. Okay, this A by B is enough. So A means this diametrical distance of the hole, and B is the capital B is this hole. I mean that is distance breadth. So I will show the graph. So this is the graph for this type of shaft flat plate. Okay. So if I know the value of A by B, I could finally find the corresponding KT. You should check the data book now. Then you will get the value. There is all this detail in the data book. You just no need to learn the whole equation. It's all written down there in the data book. Okay. So I got KT from the graph was 2.18 for whole section. Then just like usual step, we need to substitute in the our actual equation sigma max. We got 726.67 by T. So we have two maximum stress. Actually, this together, this whole and the shaft is together entity, but we are considering it into two separate part, and we have done this problem in two separate section individually, just like they were not together. So we got maximum stress developed uh, to condition as 300 by T and 726.67 by T. So among that, I need to take the maximum value. Okay, where the maximum value will be this one. So maximum stress developed is due to the hole. So we should always take the maximum condition because we are designing a shaft. So we have to take the maximum possible thing that can happen to uh, a shaft or whatever material because it should be fail proof, right? So this is a matter of safety. So we need to consider the maximum stress. That's the reason why taking the maximum stress apart from this small one. Okay, so the maximum stress is developed to the whole, so we need to concentrate on that value and develop the material based on that stress because a smaller value will come under that, right? So if I build something, prior to the failure due to the larger value, obviously the smaller one will not be coming to effect. So that's why we are taking the bigger values. So the maximum stress will be taking this value. Okay, the larger value which is due to the whole section we'll be considering. And in this question we have factor of safety. We know factor of safety is ultimate stress by the maximum stress or nominal stress, the maximum working stress. Okay, so ultimate stress is the it's a like property value of the material is also given the question. You need to decode from that given code, right? FG200, whatever numerical key value coming up with the two letter, that's a multiple stress. We have to identify that. We won't be given a separate like ultimate stress is this much value. You should able to decode that from. You should be able to understand from that. So you can see that we have 200 ultimate stress and this sigma max. I already told you uh, that's we already find the maximum value from these two value we got it. And so here I can formulate another equation for sigma max and value that is 200 by 2.5, right? So this is the actual value, 80 megapascal. So substituting mean this we have equation with the LHS same. So substituting that equation, I got the value of thickness is 10 mm. Okay, so I already know the value from this is actual safety as maximum stress is 80 megapascal, and just because to find the thickness value, I will be equating it to the this expression I obtained from the steps. So this is a way to solve this type of problem.